we're solving problem 25 from the AMC10A from 2018. For a positive integer n and non-zero digits a, b, and c, let a sub n be the n-digit integer, each of whose digits is equal to a. Let b sub n be the n-digit integer, each of whose digits is equal to b, and let c be the 2n-digit integer, each of whose digits is equal to c. What is the greatest possible value for ABC for which there are at least two values of n such that this equation is true? So, what we can do is we can sort of test things out. So, if like b was 5, if we set it to be like 3 or something like that, 3, and it just goes on for, and n is like 5 or something, then that means b of n would be 3, 3, 3, 3, 3. Stuff like this occurs. So if n was supposedly 5 and b was then this equation would be true. Now, what can we say about this equation? What we can do is we can factor out the 3. 3, 1, 1, 1, 1, 1. But is that it? Well, we're not done yet, because this can be simplified into, well, rewritten as 9, 9, 9, 9, 9 over 9. Gotta have serious brain power to think of this, which is also 3 times 10 to the power of 5. 10 to the power of 5 minus 1 over 9. So we realize here that whatever number you're dealing with in this case is always going to be b sub n is going to be equal to that same constant, which is b times 10 to the power of n minus 1 over 9. And this also applies to a, but not for c, because it's 2 times. That means c is gonna be, c sub n is gonna be c times 10 to the power of 2n minus 1 over 9. And this is true because it said cn be the 2n digit, not n. Because if cn, if c was 1 and n was 2, it would be 1, 1, 1, 1, not 1, 1. Because it's 2 times the number of digits. So this holds true. Now therefore we know what a is, which is the deal over here. So we can replace these values into this equation. So c times 10 to the power of 2n minus 1 over 9 minus b times 10 to the power of n minus 1 over 9 is equal to the square of a times 10 to the power of n minus 1 over 9. You have to square that. So we now have this very general formula right here. So what we can do here is we can sort of manipulate it, because we see here that this is still difference of squares right here. So we can rewrite this as c times 10 to the power of n minus 1 times 10 to the power of n plus 1 over 9 minus b times 10 to the power of n minus 1 over 9. And then to do this, we can do a squared times 10 to the power of n minus 1 squared over 9 squared, which is 81. we see here that we can get rid of these pesky denominators by multiplying by 81. And since 81 can be divided by 9, these will also go away. And we can also cross out all these 10 to the power of n minus 1s because it's all a common term. Now, what we get is we get that 9c times 10 to the power of n plus 1 minus 9b is equal to a squared times 10 to the power of n minus 1. We have this equation after a long time of manipulation. So what if we just multiplied out the parentheses? Then this becomes 9c times 10 to the power of n plus 9c minus 9b. And then this is all equal to a squared times 10 to the power of n minus 1. We have this equation right here, and we can subtract this term. Wait, no, this isn't 1. This is a squared, sorry. But what we do is we subtract this term from both sides, so we can get it over here and factor out the 10 to the power of n minus 1. 10 to the power of n. So we get 10 to the power of n of 9c minus a squared. And then we can subtract these to make them on the other side, which is 9b minus 9c minus a squared. So now we have this formula right here. Now we left off with this equation right here, and this is very helpful because we can determine that this is true out of 2 times 10 to the power of n. 1 times 9c minus a squared is 9b minus 9c minus a squared, and 2 when this is 10 to the power of n, 2 times 9c minus a squared is 9b minus 9c minus a squared. These are the only 2 times where this equation holds true. So if we subtract equation 2 from equation 1 and factor this out, we get that 9c minus a squared times 10 to the power of n 1 minus 10 to the power of n 2 is equal to, well, since these 2 things are the same, then this is going to be 0. So we get that 9c minus a squared is 0. 9c is a squared. So c is equal to a squared over 9 or a over 3 squared. So we found a criteria for c. Now, if we can create a criteria for all the other ones, because that's essentially what we want. The second case is where this is equal to 0. So 9b minus 9c minus a squared is 0. We can derive from that we can derive that 9b minus 2a squared is going to be equal to 0. So 9b is 2a squared. And since we already know that 9c is equal to a squared, then that means that this is going to be equal to 18c. Or simplifying, b is equal to 2c. So this is another helpful formula that can greatly help us determine. So b is 2c. It can greatly help us determine what our a's, b's, and c's are. So we can write a value of list of a's. So looking over at a, we reread the problem. It says that it's non-zero digits. So since it's a digit, A has to be divisible by 3. That yields 3, 6, and 9. According to that, we get B. Well, I'm just going to write down B. But we can derive values from C from this. So when A is 3, C has values of 1, 4, and 9. Yeah, so they also have values of that. And look at B. B is 2C. It takes values of 2, 8, and 18. But since they're digits, we know that 18's impossible. But we want basically we want the greatest sums of A's, B's, and C's. And if you were to put these in a column, 3 would be with 2 and 1, while 6 would be with 8, and 6 would be with 6, 8, and 4, and then these two 9s would be together. So when we add all these values up, well, we want the greatest value, so not all of it, but when we add the values in the columns up, we find that the greatest value that this can yield is 18. So we are done.